Okay, welcome back. Actually, last time we looked at one more complicated example. That's an example with like a system with two kinds of packets. And we consider two variations of this example. The first variation is basically we have one queue, and the packets are basically served first come first serve. In this case, while the packets are indistinguishable for packets of the same type, for packets of different types, they are totally different, and we need to take it into account. Therefore, like the order of the packets, like whether it's wet, wet, blue, blue, or like blue, blue, blue wet, wet, will be different, and we need to consider them as two different states. And because of that, the system basically become the state diagrams become very, very complicated. And basically what we did is we surrender and we say like, okay, it's impossible to analyze this kind of system using what we learned last time. So instead we look into a more kind of a simplified version of the system that we basically think of the system actually have two different queues, one queue for the wet packets, one queue for the blue packets, and then like the server will just arbitrarily pick one of the queue and serve them. In that case, we can find the steady state probabilities is given here. For this segment, I want to look into a version, I would say an intermediate version between the last two that is a little bit more complicated than the yeah, it's a little bit more complicated than the second case, but it's much easier than the first case that we studied last time. And what we consider here is a system. Again, we have two different queues, but we'll assume that the queues actually have priorities. In particular, the type 1 packets will have high priority. So in the sense that as long as we have some type 1 packets, the server will always finish serving the type 1 packets before serving the type 2 packets. And in that case, what are the states? The states will be exactly the same because we have two different queues. We can again summarize the state as the number of type 1 packets and number of type 2 packets in the system. So therefore, we can write down this two-dimensional state diagram here, very similar to last time. And then again, we can draw the state transition probability. That from left to right will be just basically we have one more type 2 packet, and that will be just lambda 2. I will omit delta this time because we all know that this delta will get cancelled eventually. Going from below to above will be just lambda 1, that we got one more type 1 packet. And from above to below will always be mu1, actually, because like the type 1 packets has higher priority, but we need to be careful that for the type 2 packets, because it has lower priority, only when we have no type 1 packets, but basically at this row here, we'll have allowed to have a type 2 packet being served, and therefore like it can move from a state on the right hand side to the state to the left hand side. So we can move to the left only when we have no type 1 packets, and we cannot do that here. So this is the state transition diagram for that one. And actually, unfortunately, okay, drawing this state transition diagram is pretty simple. As I said, like this is a little bit more difficult than the one we studied last time, but numerically it's more quite a bit more complicated, because in this case we cannot use the detailed balance equation as what we did last time. Apparently, for this state, we don't have a pair. We don't even have a pair. There's no way that the detailed balance equation will be satisfied. So therefore, we just need to do it, kind of solve the steady state probability more or less the hard way. And actually, it's very difficult to guess what are the steady state probability in this case. Okay. It won't be very easy to solve, or like can be solved like very much analytically, but at least I just want to show that it's kind of solvable. So for example, here I already revise this state diagram here, and my group these probabilities here I call let's call this steady state probabilities, like pi 00, pi 01, and so on and so forth. Here I just give another shorthand notation. This pi 00 I just call it pi 0, and this group of probabilities all the way go up to infinity will be p0 here, and this one with like one type 2 packets, and with one or more type 1 packets we call p1, and this called pi 1, and so on and so forth. Now let's look at the relationship of this pi and p here. So let's look at what is going in and out from p0 and pi 0. Just look at like what's going in and out of here, this region here. Going into this region will be just pi 1 times mu2 here. I'm getting out will be just p0 times lambda 2 plus pi 0 times lambda 2. So I have this equation here. And similarly, if I look at like what is getting in and out of p0 here, it will be p0 getting out will be p0 times lambda 2 times mu1. I'm getting in is like pi 0 times lambda 1. And with that, like basically we can represent p0 with pi 0, and we can represent pi 1 with p0 and pi 0. Therefore, pi 1 can be represented by pi 0 also. So we can see like with these two equations, we can represent pi 1, p0, or both of them with pi 0. And let's see. And similarly, let's see what is the probability getting in and out of this whole part here, p0, p1, and pi 0, pi 1. Getting out will be here, this p1 times lambda 2 and pi 1 times lambda 2. Getting in is just pi 0, pi 2 times mu2, so that one. So what we can see is like now pi 2 can be represented by p1 and pi 1. And let's look at what is getting in and out of p1. Getting in of p1 will be let's see. Okay, here on this side, that will be p0 times lambda 2 that we're getting into pi p1, right? And at the same time, this pi 1 times lambda 1, okay, this is very ugly. It's actually lambda 1 will get into this p1 region here. And getting out will be just P1 times mu1 and lambda 2. So from that, we say like pi 1, let's see. The first equation we have pi 0, sorry, P0 represented by pi 0, and this one, pi 1 represented by P0 and pi 0, and this equation, okay, pi 1 already can be represented by P0 and pi 0, therefore P1 can be represented by pi 0 as well. So you can see like this have a pattern iteratively, and then like if we continue to do that, like each of this region of probability can be represented by pi 0. It will be very difficult to solve like like analytically, but numerically we can just iteratively find the probability of all these p, and if it is probably not possible to solve it for maybe it's possible, but it's quite a bit tedious for the case when the size is infinite. But what we can do is like we can bound it like by, let's say, pretty big number and do an approximation. What I mean is like we can assume the maximum number of packets in the system are fixed to, let's say, 5,000 or something like that, and numerically we can compute like all this pi and p, and then like we can add all this up, then normalize it, then we can find all these probabilities here. And of course, like we still need to find the probabilities of each of these P10, Pi10, Pi20, Pi30 within this P0 here. But it's not very difficult. You just look at each one block at a time. For example, if we look at like getting in and out of this part here, getting out of this part will be P0 minus Pi10 times lambda 2 plus mu1, this side here. And getting into this region here will be just Pi10 times lambda 1. With that, we see that we can represent Pi10 with P0, and basically Pi10 is equal to that. And actually, we can continue to do this and find the probability of the rest of that. So, I mean, it's not very easy, but it's actually just tedious, not difficult also. And once we find all the probabilities again, like we can solve what we did, find the average number of packets in the system, and find the delay, and so on and so forth.